Data Skeptic mini-episodes provide high-level descriptions of key concepts related to data science and skepticism. Our topic for today is heteroskedasticity. How do you pronounce it? Heteroskedasticity.
That's pretty good, actually. Before we get directly into our topic, I just wanted to explore this particular data visualization that I saw online. Listeners can also see it in the show notes for this episode. Maybe you could just describe in your own words what you see.
There is a graph. What does the x-axis represent?
The average household income, presumably for a particular zip code or city that this data set is based upon.
And then what does the y say? I don't understand.
That is the average number of tickets issued per person in that geographic area. Tickets from the police, obviously.
So from this chart, it looks like the more money you make, the less traffic tickets you have.
Well, there's also one thing that's implying that. What is present in this chart that might make you
there's
think
a
that?
line.
Yeah. So if the line wasn't there, can maybe you block it out in your mind, and what do you see then without the line?
I don't know. I just see a bunch of dots. It's hard. It seems to suggest, though, as you make more money, you just get less tickets or something.
Yes, indeed. So there is absolutely a claim here. I would say that the person who created this graph is making the claim more traffic tickets are issued per person in zip codes with lower average income. Now, I have a lot of problems with this graph, and I thought it would be fun to talk them through and look at some of the assumptions. This is charting the household incomes of people against the number of tickets in those geographic areas. So we could be falling into something called the ecological fallacy, but we'll leave that for a subject for another mini episode. That's why I make the point of saying you could live there or you could be driving through there. This is just measuring the amount of tickets issued and then comparing it to the population there, which are not necessarily the same people we're talking about.
When I was younger, I didn't make much money.
Mm-hmm.
And I'll admit, I got more tickets.
Well, there you go.
I was a not as safe driver, and I made more erratic decisions, and I was not patient.
So you make more money now and you're better at issuing bribes. Is that what I'm hearing?
So nowadays, I make more money than 8 years ago, and I'm definitely a much more cautious driver because I've had so many tickets in the past. I've just decided that tickets aren't worth it. So I just don't like to speed. If something doesn't seem safe, I wait. I'm much more patient. And so, yes, I make more money, but I think the solution is that I'm just a more experienced driver.
Maybe we would say that higher income correlates with older age, as does responsibility in driving. Could that be the case?
Yeah, I mean, we could all admit there's a high percentage of 16-year-olds that get tickets.
Yeah.
And car accidents.
So looking at it that way, this relationship seems plausible. Like I said, I have some problems with this plot, and I want to first call out something called Hyman's categorical imperative, which says that before you investigate if a phenomenon is true, you should first establish, is the phenomenon even real? Here's one of the problems I have with this plot. This makes a linear assumption. It assumes that the right model to describe this is that as income goes up, that the chances you'll get a ticket goes down.
Linear?
Mm-hmm.
I don't think it would be linear, no.
Yeah, so I don't think it'd be linear either. And this is an oversight I see a lot of people make. They'll go into Excel and they'll add some just trend line without establishing if the underlying data appears to be linear or not. Actually, let's just talk more about what the plot shows. So the dots are the actual data. That part's pretty clear, right?
Yes.
And we could say the line is the person's model. That's what they think is the relationship between average household income and the chances of getting a ticket.
I mean, if you think about the average income, there's just more people who make the average income than people who are at the higher tiers anyway, so.
Yeah, so this is definitely an imbalanced sample, and we're likely to have, it appears the creator of this plot just did an ordinary least squares regression. That's going to bias towards the most dense areas of data. Mm-hmm. It's going to be less biased by the outliers. Mm-hmm. So let's talk about some of those outliers. What do you notice about the data points of highest income, above about 85,000?
They're above that line.
Yeah, all of them, right? Another way to say that is that this model consistently underpredicts for all high incomes. Do you think that's a property of a good model?
Well, I don't know. You said on previous shows, if it's too predictive, it's a bad model.
Yeah, what you're referring to is the risk of overfitting. I definitely would not say this overfits the data. Does it underfit it, maybe? That would be the claim of assuming it's linear when it's not. But let's also look at the lowest data points. What can we say about all the data points making below 40,000?
Well, they're all above the line too.
Almost all of them, yeah, all but two. It seems that this fit doesn't adequately capture incomes below 40,000 or incomes above about 85, leading us to believe that maybe a linear fit wasn't the best choice for this. Now, there's another thing we do more generally is we look at what are called the residuals. We've talked about that before, but I'm not sure if we talk about it enough. Do you know what residuals are?
No, but I would assume it means left over.
Left over after you subtract the actual observed data minus the model's prediction. So imagine each of those dots, the model's trying to predict those. Measure the difference between the dot and the line, and you get the residuals. That's the amount of error, what the model is not accounting for. So whenever there's a pattern in the residuals, that tells you that your model failed to account for something. Because if your model accounted for everything that's predictable, your residuals would look like white noise, just random data. That leads us to this other point. What I wanted to talk about here is heteroskedasticity. So heteroskedasticity is the circumstance in which the variability of a variable is unequal across the range of values of a second variable that it predicts. Is that a clear definition for you?
No, I don't know what that means.
Let's say you asked a bunch of people to measure a pencil, and they all had different rulers, right? Everyone has a different tape measure at home. How much do you think their measurements would vary?
Everyone's pencil is a different length if you think of the old-fashioned pencil. But if it's a mechanical pencil, they're probably all the same length.
Yeah, so let's say they all have the same mechanical pencil. Although, good point, there's variance due to manufacturing, and there's also variance due to the measurement.
Oh, okay. They probably give or take, like 5 millimeters.
It'd be very small variance. That's the variance. Now, what if, on the other hand, you ask them to identify a neighborhood cat and measure its length from nose to tail?
So it's any neighbor's cat?
Yeah, any neighbor's cat.
Well, that will vary greatly.
Now, what do you think if we separated the cats by how old they were? Do you think there's as much variance in kittens as there are in adults?
I don't know. I don't look at kittens' tails.
So I'm going to go out on a limb and guess that kittens, there's less variance because they're all, there's a certain maximum size of a kitten, right? I don't know what the biggest kitten would be, but even humans, no human is born 3 feet tall. So since they're smaller, there's less of a chance for variance there. Whereas as they get to adulthood, you start to see different genetic traits and breed traits where you can have really big cats like a Maine Coon and really small ones and stuff like that. So the variance in size increases as the age of the cat increases, up to adulthood, I presume. That is heteroskedasticity. It's when the variance is conditioned on some other variable, in this case, age. Heteroskedasticity is another thing surprisingly, actually, you can ignore it a lot and get pretty far because it generally won't bias a fit like the ordinary least squares regression we see here, but it does definitely screw up analysis of variance that we talked about kind of recently. Heteroskedasticity is one of those things you have to check for in your data and sometimes try and smooth out, like maybe with a logarithmic transformation or something like that. So truth be told, it's one of those things that's not the greatest crime to ignore, but it's something a good data scientist should be aware of in their data.
Is that bad?
Well, it's something you should account for. Data is neither bad nor good. It is what it is. As long as it's correct, it is the data. It's our analysis of the data that counts. And if you fail to account for heteroskedasticity, that is bad because you may arrive at a false conclusion because you're using a method that assumes homogeneity of variance across a data set. And if that assumption fails, then your analysis is on shaky grounds. Thanks as always for joining me, Linda.
Thank you. For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on iTunes or Stitcher.